Let's see. The original schedule today had Colonel Gordon Fullerton was going to come and talk to us about both cockpit design, but primarily about test flying the shuttle. Unfortunately, he is in charge of flight operation. Well, not unfortunately, he is in charge of flight operations at Dryden Flight Research Center for NASA. Unfortunately for us, since the time that we had agreed on this date, they scheduled at the beginning of next week a major base inspection. And if any of you are connected with the military, you know what that involves. And since he's head of flight operations, he really has to be there, make sure that they're ready for it. He has rescheduled. He will be here in November, and I'll make adjustments to the syllabus. So let's see. On Thursday, Bob Reed is going to talk about aerothermodynamics. And what I thought I would do today is kind of a potpourri, maybe doing a little bit of a recap on where we've gotten to so far, and also I brought a few videos just to give you, a visual reminder of some of the things that we've been talking about with the shuttle. Any sort of general questions about what I handed back to you? I'm happy to meet with teams individually to discuss any specific questions, but okay. Let's see. One thing that hi Ellie. I was just telling the class Gordon Fullerton was supposed to be here, but he's had to postpone until November because they're having a base inspection of flight operations, so he's not here. I had an email from Professor Cohn, who will be here. Now let's see if this is, yeah, okay. He had an idea that now that we've kind of started going into details on various subsystems, that it might be interesting to work our way through a shuttle flight and just remind ourselves of the different subsystems that are brought into play at various times during a shuttle mission. This is kind of part of the systems integration process, and remember that we talked at the beginning how in the systems engineering process we always want to keep in mind the eventual operational use of the systems that are being designed. So the idea, for instance, would be, start at the very beginning. You're sitting on the pad. You could even go further than that, because remember we talked about how a lot of systems had to be developed, for instance, for loading the payload into the cargo bay. They have that big payload change-out room. They had to design the hypergolic reaction control and ohms motors in such a way that the pods were actually removable from the shuttle because they were using hazardous hypergolic fuel, and they can't be serviced in the main hangar. They have to be taken over to a remote section of the Kennedy Space Center. So there's a lot of, and then of course the servicing of the tiles. There's a lot of servicing, maintenance work that has to be done on all the subsystems, and that has to be, ideally, it should be designed in from the beginning. Of course, in many cases, we got a lot smarter after we started to use the shuttle, and if we were doing it again, which is something that you'll be thinking about, we would, in fact, have built certain things into the subsystems which would have made it easier for them to be maintained and repaired. So what I'm going to do, just as an experiment here, let's think briefly about these subsystems, and I've got a little video taking us through the launch and the entry stages, and then I have one or two other things to show you, and which will just illustrate certain other aspects of the shuttle mission. So right at the moment of liftoff, just kind of to set the stage, the final countdown starts at T-minus 9 minutes. They typically will have holds built into the count, so that if you're going, particularly when you're going for a very tight launch window, like if you're on a rendezvous mission to the space station, you have to launch when the space station basically is pretty much going overhead. And since the space station is in a 51-degree orbit, it takes more energy to get into a 51-degree orbit, because normally if you launch from Cape Canaveral, hopefully you understand the orbital dynamics. If you launch due east, you get the full speed of the Earth's rotation. And since the latitude of Cape Canaveral is 28 degrees, that puts you into an orbit which is inclined 28 degrees to the equator. And that's what we did when we did a rendezvous with the Hubble telescope, which is in at 28 degrees. In fact, I remember my brother was telling me we launched about 4 a.m., so it was night, and just about 20 minutes before we launched, they saw Hubble fly over, and everybody thought, oh, that's a good sign. They seem to know what they're doing. The thing is that you know, when you have an object that is in orbit, and the orbit you can think of as being roughly fixed in inertial space. Obviously, it precesses a few degrees every day, but if you think of it as fixed in inertial space on the time scale of a day or so, then the Earth is turning underneath it, and you have to launch basically when you're in that orbital plane. Now, if you have a little bit of extra energy to burn, you can launch a little bit earlier or a little bit later and use that extra delta V to change your velocity to get into that plane. So if you're launching to rendezvous with Hubble, say, which is in a 28-degree orbit, you have a bigger launch window than you do if you're launching to the space station at a 51-degree orbit, because going into a 51-degree orbit, you're using a lot of extra delta V just to change from a 28 to a 51-degree inclination. So the launch window to rendezvous with the space station is very short. It's only about 5 minutes. So in order to make sure that they have the maximum time to the maximum chance of making the launch window, they actually build in some extra large holds, even more so than for a normal launch. But you pick up the final count at 9 minutes. The shuttle at that point is on external power. At about 7 minutes, the pilot, that is the person sitting on the right-hand side, who should be called the co-pilot, and I've talked about this with a few of you. None of the astronaut test pilots, these are kind of big ego people. Nobody wants to be called a co-pilot. So the person sitting in the right seat is the pilot. The person sitting in the left seat, who's really the pilot, is called the commander. Just to clear up the pilot does not fly the shuttle, except for usually if you have a nice commander, he'll let the pilot when you're pulling away from the space station. It's kind of a tradition that you give the pilot the stick and let the pilot do a fly around. And in the old days, some of the commanders actually gave the pilots a little bit of stick time before landing, but that generally doesn't happen now. Anyway, the pilot is in charge of a lot of the subsystems, the main engines, the electrical power system, the auxiliary power units. So it is the pilot who has to throw a switch to put the shuttle on internal power. So at about 8 minutes before launch, you go onto fuel cell power. Then at about 5.5 minutes before launch, you turn on the auxiliary power unit. Remember, we talked about that subsystem. That generates the hydraulic pressure to move the flight control surfaces and the main engine bells. And you'll see, if you watch a launch sequence starting at about 3 minutes after the auxiliary power unit comes on, and at that point you can sort of you feel a little bit of humming in the vehicle when you're sitting in it. They then move the engine bells back and forth through their entire range just to make sure that the hydraulics are working, and you can actually, the whole shuttle shakes when that happens, so you can sort of feel that when you're sitting there. And then of course, one of the challenges with a cryogenic engine, and this is going to be an interesting development project for the future when they want to have restartable engine. Remember, these are cryogenic engines, and so you have to do a cool down. And so you start to flow the liquid oxygen and liquid hydrogen through the piping. So inside a minute, there's you can feel kind of a rumbling down below as valves are opening and things are starting to flow. At 31 seconds, the Launch Control Center gives control over to the shuttle computers. And the last 31 seconds are controlled entirely by the shuttle computers. They look at, thousands of data points to make sure that everything is working properly. At T-minus 6 seconds, the engines go through an ignite sequence. The engine starts are staggered, and you'll see that when you look at the slow motion of the video that I'm going to show you. That reduces the shock on the system. It only takes a couple of seconds for the engines to come up to full power. You certainly don't want to commit yourself to lighting the solid boosters unless you're 100% sure that your main engines are firing, because if even one main engine is not operating at 100% efficiency, you cannot make it to orbit. In fact, if you have one engine out on the pad, you have to do a return to launch site abort. We'll talk about the details of that whole process at some point. Yeah, Dan.
When's the last second that you can abort launch?
You can abort launch right up to when the solid boost. Once the boosters are lit, you're going. And just hope you're pointed in the right direction, because there's nothing, there's no thrust termination on the solids. So, and it has happened 4 times that we've had pad shutdowns. The engines are monitored. On 2 of those occasions, it turned out that the problems were instrumentation. On 2 occasions, it turned out that there were, in fact, real engine problems. And I'd say, for a 50% success rate, you're doing well. I mean, it was the right thing to shut down the engines all those times. Although the very first time when they had an engine shut down on the pad, well, first of all, just an acronym is MECO, Main Engine Cutoff, which normally happens about 8.5 minutes after launch. So the comment by Steve Hawley, who was the flight engineer in the center seat when they had this was on the 14th shuttle flight, and they had a pad abort. His comment was, somehow I thought we'd be a little bit higher at MECO. And it turned out that they didn't realize it at the time, but they actually had a hydrogen fire on the pad. That there was remember we talked about how there's a lot of hydrogen, and of course before the engine ignition, we have those sparklers to get rid of the excess hydrogen. But in the process of shutting down the engines, there was also a lot of excess hydrogen which got into the engine bay. And the problem is that a hydrogen fire, as you know, is pretty much invisible. And they didn't have any infrared cameras at the time. And so, basically everybody went around, the crew went about their, took their time, and everybody went out. And once they realized it, they put on a water douse, and now we have infrared cameras, and people, whenever you have an engine shutdown, you have to be very careful that you don't, in fact, have a hydrogen fire. Coming back to the subsystem. So the last stage of the launch, the main engines have gone on. You have turned on the hydraulic system both for the main engine, and the boosters have their own hydraulic systems, and the boosters have their own auxiliary power unit. Guidance, navigation, and control, of course, is absolutely critical. Now, first stage is what they call basically open loop guidance. There's a specific trajectory that you're supposed to follow. Once the solid boosters are off, you're following a closed loop guidance, which is taking you to a specific point and velocity in time and space, and the trajectory is actively adjusted to get there. Because the solid boosters have so much thrust, you don't want to do a lot of sporty maneuvering. In fact, the biggest challenge from maneuvering point of view is when you're going through max Q and maximum dynamic pressure, and you have to relieve wind shear loads and on the aero surfaces. Basically, when the boosters are firing from the crew's point of view, it's hands off. There's no way that you could take manual control over the boosters. There's just too much power, and just a little bit of deviation from your course, and you'll break up aerodynamically. So it's hands off. The fuel cells are generating all of the power. The guidance, navigation, and control is being done inside the shuttle, and the results are sent to the solid boosters. The solids, the gimbals can move. So the roll maneuver, for instance, is done by the solid engines.
How do the solids gimbal?
The solids can gimbal, yeah.
How do they gimbal?
The same way that the main engines. I mean, they're on a mounting with hydraulic actuators, and so the actuators expand and contract, and yeah, you can imagine the forces that are involved there, because these are 2.5 million pound thrust engines. It's pretty amazing. Going through maximum dynamic pressure, SRB separation, main engine cutoff, basically the same systems are working. The critical things are, of course, the main engine has to be throttleable, so that this was a big challenge, as we heard, in making the main engine. It's throttleable for two reasons. It's going through a maximum dynamic pressure, and at that point the solids are also the way the solid propellant is loaded, the actual cross-sectional profile is such that you don't have a constant thrust profile. The thrust profile is very high right at liftoff, where you need a lot of thrust. It falls off as you're going through maximum dynamic pressure, and then it builds up as you burn through the last 2 minutes of SRB firing. The shuttle is pulling about 2.5 Gs at SRB cutoff. The aerodynamic separation of the solids got a lot of attention. To have a recontact would be a disaster. So you have 4 separation motors, 2 at the top and 2 at the bottom, which basically push the solid boosters away from the shuttle. And of course, those motors are pointed right at the shuttle in order to move the boosters away. So it's pretty spectacular, when you're inside, especially at night, because you have all of this. They're little solid rocket motors, and they're firing right at you. So visually it's spectacular, but it also unfortunately leaves kind of a nasty coating on the front windshield, most of which luckily gets burned off during re-entry. But the pilots were a little bit concerned that might hurt their visibility in landing, particularly if you had a bad sun angle. So they always try to consider the sun angle for landing as well as winds. After SRBs come off, now you're back to about 1G. You have second stage guidance, which is closed loop. You're sensing acceleration and orientation. And nowadays, they often fire the OMS engines for part of liftoff as well, just to get a little extra oomph when they're going up to the space station. So that's another system which is brought into play during ascent. Then you get into after MECO, 8.5, 8 3/4 minutes. Now you have to get rid of the external tank. And you've got a lot to do to basically to power down the main engines. Remember, you've been burning liquid oxygen, liquid hydrogen. You've got a tremendous amount of ice which forms in the engine. I have some pictures to show you of what that looks like when you get into orbit. Also, you've got thousands of pounds of hydrogen and oxygen left inside the pipes. And if you just close your valves, eventually that will all vaporize, build up pressure, and it actually could cause an explosion. And so one of the first things that you have to do when you get into orbit is to vent the main propulsion system. Let's see. Actually, Professor Cohn did not put on RCS here, which is absolutely critical, because you have explosive bolts to separate you from the external tank, but basically the external tank has no propulsion on its own, so you on the shuttle have to fly away from it. So you use your plus Z, that is the downward thrusters. And remember, we talked about how the shuttle has two RCS systems. It has the primary systems, which have about 850 pounds of thrust for each thruster. And then once you're in orbit and you don't have to do a lot of propulsive maneuvering, then we shut down the primaries and we use the verniers, which only have 25 pounds. That takes a lot less fuel. But those primary thrusters, we use not only the ones in the aft, but in the forward, so that you have balanced thrust. You know, if you're trying to move away from the external tank, you want to fire the thrusters both in the nose and in the tail so that you move straight up. Well, you know, we're sitting up in the nose, and when those thrusters go off, I mean, I've never been in a war or a battle, but it strikes me as the sound is what you would get if mortar shells were exploding around you. I mean, it's just a and it's you know, right after riding through you know, through launch, first thing happens, you go weightless, but then the next thing, you know, you're hearing these explosions all around you, and it's it can be quite exciting. Actually, I'll just share a story with you. On my first flight, they decided to do a special kind of a test, and instead of having there's fill and drain valves for the main engine on the side of the shuttle. Usually we vent the propulsion out through the engines themselves, but they wanted to look for a quicker way to do it. So let's see, this was the 16th shuttle flight, was my first flight, and they gave us what they call a detailed test objective, where right after external tank separation, we opened the side fill and drain valve. And I remember the commander asked some of the guidance and control people, is the shuttle RCS going to be able to compensate for the extra thrust that you get? Said, yeah, no problem. We've done the calculations and it looks fine. And this is the reason why you do tests, because in fact what happened was we came off the tank, opened the fill and drain valve, and the shuttle rolled over 90 degrees, and the RCS jets started going like crazy. So to try to correct us. And so they were in a force fight with the, and after about 15 seconds, the pilot said to the commander, do you think I should shut the valve? Because, I mean, the noise was incredible. It was just like I say, it was like you're in the middle of a battlefield. And at that point, the commander said, well, it's too late now because we had gotten through most of the disturbance, and we did recover and got to normal attitude. But it was pretty exciting. And the point is that at that point, you're in a transitional state. Your computers are still in the launch configuration. You have your primary RCS, and what you have to do is transform the shuttle now into an on-orbit configuration. The shuttle computers are so ancient, and has anyone here ever, never mind used an overlay technique, but even heard of computer overlays? No, I didn't think so. Back in the old days when computers had rather small memory and you had to run large programs, what you would do is you'd have your entire program, well, originally it was on punch cards and then eventually on magnetic tape, but you would segment your program, and then you would load the first part of your program as much as you could fit into memory, run that, save the results, load the second part, transfer the results, run on that, and so on. Well, believe it or not, that's the way the shuttle computers still operate. We have it's an overlay system. They can't hold all the software for the entire flight. So we have a launch overlay, an ascent, an on-orbit, and an entry. Now the backup flight system is stripped down, and so the backup computers hold the software for the entire mission, but there's a lot of things that they don't do that the main computers do. So what you actually have to do is perform what they call a major mode transition, which basically means you punch a few buttons, tell the computers to go into orbit mode, and then all the screens go blank. I mean, it's a very kind of a strange feeling, and you just have to sort of hold your hands and not touch anything for about a minute or so while the tape recorders are spinning down in the guts of the shuttle and they're loading the stuff onto the shuttle computers. Now I think they upgraded the tape recorders to solid state, I believe. That's correct, isn't it, Ellie? I don't think they do you know that? I don't think they use tape recorders in the shuttle anymore, but they did in any case at the beginning. So it was, yeah. I mean, just maintaining this computer system has been a big challenge, and then you get into the orbit configuration, and yeah, in the ascent configuration, your Vernier RCS isn't even enabled, but and inside the ascent configuration, of course, you have not just your nominal ascent, but you have all of the launch abort modes: a return to launch site, a transatlantic abort, and a abort to orbit, or abort once around. All that gets flushed. And now you're on orbit. Your on-orbit software does not give you the ability to do entry and landing. You're going to have to redo another overlay, or what we call major mode transition, before you do that. Okay, well, we've gone, yeah.
So you're talking about how it's already started the computer to return to launch site or transatlantic
Right.
Landing.
Right.
There are several different landing spots, right?
Right.
At least transatlantic.
Was one picked for every?
There's always one picked as a prime, but you have the ability to redesignate depending on where in the ascent you run into a problem.
So all options of the computer.
All options are available. Yeah. But there always is a prime transatlantic abort site which is chosen. And usually what happens is, there's several transatlantic launch sites, Sometimes one or more of them is down because of weather. And in fact, if all of them are down, even if the weather is perfect in Florida, you scrub because you need to have an abort site. Okay, I'm going to show you a video now. Let's, do I have a, there's no Panasonic controller, so I guess I have to do that by hand. I'll just go back to the very beginning. Okay, so I'll try to walk you through some of these. Let me just see if no, that really doesn't work. Okay, so remember this. That's the water deluge to stop the shock wave coming back. Now you have the staged combustion. These are the OHMS engines, the RCS, and the main engines. Remember we talked about the off-angle thrust. Those are the bolts which hold the solid boosters down. They have to go, they all have to fire, all 8 of them have to fire at exactly the moment of SRB ignition. If you watch closely, when you see it go up, you can actually see it sort of moving that way, again, because of the off-angle thrust of the main engine. This is the roll maneuver, which puts you, you go over on your back, headed towards the proper orbit. And then as you go through max dynamic pressure and break Mach 1, you often get those condensation trails. Okay, so this is a pilot's eye view now of a shuttle launch. That's the roll. This is speeded up by a factor of 2. So that was the roll maneuver and the Florida coastline. And I always thought one of the amazing things was actually how fast the blue sky turns black as you're going up. SRB separation, you're up at an altitude of about 20 miles. And you can see up there that very quickly, the blue sky of Earth is turning into the black of space. This launch was a high inclination launch, so they were actually going into a 58-degree orbit, so they flew literally right up the eastern seaboard. Well, there was it was a Space Lab mission, I believe, and one of the things they were going to do was observe the Earth, so they wanted to get into as high an inclination as possible. Okay, now remember when Bass Red was talking about the aerodynamics of the shuttle, he said one of the things that they never were able to get quite right was the plume, and he talked a lot about the angle of the skirt and how that affects the aerodynamics of the plume. And you can watch how the plume is continually changing as you are getting higher in the atmosphere and you have less and less pressure. You also notice some of the flames are getting sucked back. In between the shuttle and the external tank, of course, that's where we have the problems with the foam shutoff. You've got supersonic shock waves bouncing around, so it's a very, very nasty environment in there. And you see when the external tank comes off, often there's a lot of area here which is charred and burned out just because of the shocks. You can see now that the plumes are tremendously expanded. The other thing that well, I'll wait until after SRB separation. As I say, you're up to about 2.5 Gs at this point, and now you can see that the solids are starting to tail off. You can see a qualitative difference in the flame pattern, and now you can definitely feel this inside. You see the separation motors, the boosters fall off, and as you know, they were recovered. Making sure that the thrust tail off matches, as we heard, was critical. Now here's a picture from a belly camera of the boosters falling off. Okay, so now the main engines are firing. When this happens, I'll just stop it for a minute. Pause. So I don't know if you've seen pictures of Saturn launches. They actually have some of the most beautiful patterns of the re-entrant plumes. But the plumes, as you get up into a vacuum, the exhaust plume expands, and it actually folds back around the vehicle, which is, it's not a danger to the vehicle, but visually it can be quite spectacular. On the first night launch of the shuttle, during the day, the plume is so faint that you really can't see it from outside the windows. The only thing from the ground, you can see the bright points when you're looking right at the tail of the shuttle, but you don't actually see the plumes. The second flight engineer, who has a good view out the overhead window, about 5 minutes into launch, he asked the pilot, who's in charge of looking after the main propulsion system, everything okay with the engines? Yeah, everything's okay. And about 6 minutes, everything okay with the engines? Yeah, everything. And after they were on orbit, pilot asked him, why did you keep asking me about the engines? Everything was fine. Well, apparently the guy had been looking out the overhead window and had seen flames starting to come out, which is essentially the expanding plume. And of course, it was the first night launch, so nobody had ever seen that on the shuttle before, and so you're always looking for something off nominal. But as it turned out, it's just normal plume behavior. So now we've got a few minutes riding on the main engine to build up to orbital velocity. So essentially we're flying up the eastern seaboard, and it will give you some sense of the acceleration. Hopefully you'll recognize some of the geography. When they talk about taking the shuttle from Washington to Boston or back, this is the real thing. So it takes about 8 minutes, 8.5 minutes to get from Cape Canaveral to Cape Cod. So there's Long Island coming up.
I heard Plattsburgh, New York was a alternate landing site.
Mm-hmm. And so we're really moving at this point. You're going about five miles a second. Orbital velocity. There's Cape Cod, and now you'll see a little bit of a pitch as we separate from the tank. And here again is the belly camera as the tank comes off. And you can see these little charred patterns in here. That's where the big piece of foam came off, which destroyed the Columbia. Okay, so on orbit, let me stop it here. We've talked about for its orbital operation, It was all the different things that the shuttle was supposed to do that really drove the design. Speaking of which, I guess how did things go last Thursday? Colonel Young gave the lecture on the military. I haven't had a chance to talk with him yet, but hopefully maybe he had some new insights or things. I know we talked a lot already about the military requirements, but you know, in addition to launching large satellites, you know, of course we've repaired satellites, we've done science experiments, we've done a lot of educational activities, and I'm not going to deal with those subsystems so much now. Remember that the computers now really don't deal with the main propulsion system anymore. The only thing that you have to be concerned about generally in orbit, you still have to maintain thermal control over all of the parts of the shuttle. So the thermal subsystem is very critical. We talked about the problems with hydrazine. If hydrazine freezes and then it expands when it thaws, and it can break the lines. Hydrazine leaks are very nasty. We had one instance on a shuttle flight where one of the thrusters did develop a leak, and you could just see the exhaust coming out of it until they shut off the isolation valve. There are several sets of RCS thrusters, each of which is connected to the tanks by a set of isolation valves. So you have essentially triple redundancy in your reaction control system. And if any one of the systems develops a leak, you can isolate individual thrusters to tell them not to fire if it's a leak which only occurs when you fire it, or you can shut down an isolation valve for an entire set of jets. I won't go into great details, but you know, we talked about the importance of redundancy, and that's one of the ways that it's built in. Let's see, what else do we want to say about subsystems during orbit? What are some of the other subsystems which get called into play for orbital operations?
The environmental subsystem.
Environmental, and that
Is
of
that
course.
controlled by the computer, or is that kind of its own separate automated?
A little bit of both. There are, for instance, pressure valves are mechanical, so that they'll open at a specific pressure mechanically. Both, you know, if you have an overpressure, or you set your, we have different settings. The normal setting is for sea level atmosphere, and of course you have to balance the oxygen and the nitrogen, and so there's a fairly complex algorithm. Well, not it's fairly simple, I suppose, but there's an algorithm which senses both the overall pressure and the oxygen partial pressure, so that if your pressure goes down a little bit, the system has to know whether to open up the oxygen valve or the nitrogen valve. Also, if we're going to be doing extended spacewalks, and I'll be giving a talk on the airlock and the spacesuit and the other systems that get involved in spacewalks, so I won't go into that in detail here, but we actually have to bring the cabin down to 2/3 of an atmosphere, 10.2 pounds per square inch. We keep the partial pressure of oxygen at sea level, so that raises the oxygen concentration to about 30%. And the reason we do that is to purge the nitrogen out of our bodies, so that you don't get the bends when you go down to the 4 psi, which is at pure oxygen, which is what we run our suits at. At that point, we actually have to trick the system into, because they didn't build in a 10.2 controller. They have a 14.7 psi controller. but in any case, we control manually, and we basically bring the cabin down to 10.2 psi. Humidity control. We have the water system. Of course, we make a lot of water with our fuel cells for the electrical power system. There's 5 different water tanks. One of the tanks is sterilized for drinking. In the early days, they put a lot too much iodine in the water. In fact, when I came back from my first flight, my teeth were totally brown. The dentist had a fit, and they actually have cut back on that. And the water is actually reasonably palatable at this point. You couldn't drink it early on unless you mixed it with Kool-Aid or Tang or something, which is even worse, but that's another story. The rest of the water tanks are, there's just a lot more water than anybody can drink, and so we basically, those are called supply water tanks, and we use that water for cooling. Remember, that's another part of the environmental control system. And, we've talked about all of these a little bit. This is just kind of a review. Remember that during ascent, once you get above 100,000 feet, and during the early time on orbit, we get rid of excess heat by water boiler. Now, it's an interesting system, a multi-component system. Out in the cargo bay, we use Freon to bring the heat through the radiators. First it goes through the radiators, and so once the payload bay doors are open, particularly if you're pointed away from the sun, you can radiate a lot of heat. After the Freon runs through the radiators, if it's still hot, it runs, you can activate the water boilers. And so if the payload bay doors are closed, or if there's some problem with the radiators, and you need excess cooling capacity, you activate the water spray boilers. Now the water boilers use water, if that's your only cooling system, they use water at a rate faster than the fuel cells produce it. So if you can't get your payload bay doors open, and that's part of the whole mechanisms, remember, which Henry Pohl talked about, if you can't get your payload bay doors open, within a few hours you have to turn around and come home because you'll run out of water. So now, on the other hand, how do you get the heat out of the crew cabin? You don't want Freon running around the crew cabin because it's nasty stuff if you develop a leak. So there's actually there's 2 ways. First of all, you circulate the cabin air, which gets heated up both by the people and the electronics, and you run the cabin air through a heat exchanger where it dumps its heat into a cold water loop. And the cold water loop takes cabin heat, and then the cold water loop is also circulated by some of the electronics. Some of the electronics are air-cooled, and of course there's no convection, no density-driven thermal convection in weightlessness, so you have to have forced air convection. So there's fans all over the place blowing air at the electronics and at the crew as well. And these are all small fans running at very high RPM, and so they tend to be very noisy. And so, in fact, the typical environment in a space cabin is dominated by high-pitched fan noise. In fact, it gets so bad in the Russian Mir. We found this once U.S. astronauts started to fly up there. It was actually causing permanent hearing damage in a lot of crew members, and people were having to wear earplugs or headphones while they were working near some of the equipment, which is not from a human factor's point of view, is to have earplugs in and then somebody tries to call to you from the next module because there's an emergency. That's not a good deal. Yeah.
Do you get a lot of electrical interference because of that? Do you see high pitch?
No. There are a lot of electrical signals up there because the crew uses wireless headsets, but everything is checked for electromagnetic compatibility. And in fact, if you try to fly a payload on the shuttle or the station, you have to pass a lot of EMC compatibility testing. So then, anyway, the water from the cabin, which is taking the heat both from the air and the electronics, is then passed through a water freon. It's taken out of the cabin and passes through a water freon heat exchanger, and then the freon takes the heat further aft, where it's dumped into the radiator or the water spray boiler. Cabin air revitalization. We rebreathe the air. It's not like in scuba diving where you take a breath of air and then you just blow it all away. We can't afford that, so the air is rebreathed, which means you have to scrub out the carbon dioxide. The shuttle is not designed for long duration, and so we use lithium hydroxide scrubbers. Lithium hydroxide plus carbon dioxide makes lithium carbonate plus water plus heat. And so those are canisters which have to be replaced twice a day. And in fact, the preparation for replacing the lithium hydroxide scrubbers is you have to turn the cabin fans off so you don't get a lot of air going through the cylinders where you put the scrubbers. So for that 1 minute, you can actually appreciate the peace and quiet of being in orbit, and then you turn the fans on again and you realize how noisy it is, because after a while you get used to it and you don't hear the noise until you turn it off. So that's let's see, air revitalization system, humidity separation. You're pumping out a lot of humidity in your sweat. And that is put through a cooler and essentially a centrifugal, they call it a slinger, which gets rid of the water, and that goes into the wastewater tank along with urine from the waste collection system, and that's also dumped overboard. There are separate dumps for the supply water and the wastewater. When the water is dumped overboard, of course, up in orbit, the pressure is below the triple point of water, so liquid water cannot exist. So you either have gaseous water vapor or ice, and so as soon as the water comes out the wastewater dump valve, it solidifies, and you get essentially a snowstorm blowing away from you. And if the sun is lighting it up in just the right way, it can be quite spectacular. If I have time, I'll show you a picture of that. Let's see, other on-orbit systems. Of course, we have the payload systems. We talked about the remote manipulator, the robotic arm. Anything else? Yeah.
With the flight deck, what's happening there, especially with the forward flight deck, which is mostly used during launch and entry?
The crew uses lots of checklists and cue cards, and so typically the center of the front cockpit has mostly the airplane type controls, which you use for flying the shuttle. The systems controls tend to be around the sides, and then the controls for doing rendezvous and operating payloads are in the aft part of the cockpit. So yeah, the forward center cockpit is not used very much when you're on orbit. Overhead panels is mostly ohms and RCS, and then electrical stuff is over the right, and environmental control is over on the left. And
so when you're docking with gear or something like that, the pilot commander looks up the back.
yes, During the early phases of the rendezvous, when you can't see anything, typically the commander and the pilot will sit in the front seats. But once you get close enough to have visual contact, you typically you don't approach straight on. You typically approach with your payload bay pointing towards the object you're rendezvousing with. And that way you have the rendezvous radar can pick it up. There's a rendezvous radar system, KU band radar, which is on the starboard side, and there's also star trackers which can pick it up when it's farther away. And then visually, you just look out the overhead windows, and so you control the final phases of the rendezvous, which we call proximity operations, from the aft flight deck. And there's a controller stick there, and actually it's interesting that this is part of the human factors, both for controlling the manipulator arm and the shuttle. You can actually there's a switch. For instance, there's a translational hand controller and a rotational hand controller. The translational, is to make the orbiter go in plus or minus X, Z, or Y. If you're normally you think of the shuttle when you push the stick back, you want the shuttle to go in the direction of the stick. And so that would be a plus or minus X, which is along the long axis of the shuttle. And that's the way the forward controller works. And you can set the back controller up so it's just the inverse of the forward controller. So when you push in the stick, the shuttle goes backwards. But when you're actually looking out the window and you see the object, the space station or Hubble or whatever you're rendezvousing with is ahead of you, and you want to go towards it, you'd like to be able to push the stick. And so what they've done is that so here's the upper window, and they have the stick actually at an angle. So depending on how you set the switch, you can make it so that when you push on that stick, it gives you a minus X, or you can put it in the Z mode, so when you push the stick, it gives you a minus Z. And that's a nice human factor thing. They have a similar situation for the manipulator arm. On the end of the end effector, when you're coming into a grapple fixture, and there's actually 3 wires, and if you're looking here, there's 3 wires inside the end effector, and those actually are moved around like so that they tighten up over the little knob. But there's a camera up here, and then above the grapple fixture, there's kind of a bullseye with a little stick on it, so that the stick is like this, and if you're off to the side a little bit, you can see by the angle on the stick both how you are in translation and in the attitude of the end effector. The thing is, when you're actually flying the end effector and you're looking out the window, when I'm just looking at it, I might want to be able to push the translational hand controller, and the end effector will move away from me in the cargo bay. So that's called a shuttle coordinate mode. And they have a nice setup. Again, this was from a lot of human factors studies. You can then go into a different mode when you're actually bringing the end effector right up to the docking fixture, where you switch over into what they call end effector mode. So now I actually, I'm looking in the television picture, and I see, this image, and I want to correct it, and I want to move to the side a little bit and go in, but I want to do that in the frame of reference of the end effector. And so by going into end effector mode, when I'm working the translational and rotational hand controller, it actually works around that coordinate system. And there's actually 2 other coordinate systems for different types of payload operations. So they've done a lot of work in these systems to essentially to use computer-assisted modes to make it easier to operate both the robotic and also the shuttle rendezvous and docking system. What else do we want to say about on orbit? That'll probably do it. Let's take a 2-minute break, and then we'll move ahead to entry. Enough of a stretch. Yeah.
Before we leave the on-orbit
Sure.
part, how much of the cruise time is taken up with changing the carbon dioxide scrubbers, dumping wastewater, just the general, like, we got to do it to survive stuff, versus percentage of time to...
Typically, one person can take care of most of the on-orbit just maintenance activities. You have to do things like periodically check your filters. There's, every 1 or 2 days you have to go through with a vacuum cleaner and clean your filters. You have to change the lithium hydroxide. There you want somebody to help to turn off the cabin fans while the person downstairs is changing them out. Periodically clean the toilet, prepare food. I'd say more or less one person around the clock can take care of most of the things that have to get done if nothing goes wrong.
Kind of alternate between the members.
Yeah. Typically, you can have either a 1-shift or a 2-shift flight, depending on whether your payload requires 24-hour operations. And typically, the pilot and the commander are considered to be the orbiter crew, and so they'll take care of orbiter-related things, and other people concentrate more on the payload or doing spacewalks or whatever the mission is about. Everybody is more or less trained to perform maintenance activities, so you can share the load, but typically with a crew of 6 or 7, you have the luxury of specialization. Let's see. I spoke at length about what goes on during entry, so I'm not going to go through all that again. I'll just run the video here to remind you. But do remember, again, before you're ready to do your deorbit burn, once again you have to reconfigure your computer system. So, again, everybody gets in their seats, hands off, because you don't want to throw any switches, or you definitely don't want to touch the computer while it's going through this major mode reconfiguration. It's sort of like, when your computer is booting up, you don't want to mess anything around. You just keep your hands off. Once you're in the deorbit and entry major mode, that is actually then subdivided into submodes, where one of the software loads controls your deorbit burn, and then another one is in effect while you're essentially in free fall before you hit the atmosphere. And then once you hit the atmosphere, you go through a series of submodes depending on your altitude. And remember, we spoke about how the flight control system continually has to upgrade its flight control laws depending on the atmospheric condition, and so you need to know your nav state. And then finally it switches into the final approach and landing mode when you go around the heading alignment circle. That's the final step, which I don't think we talked about. Remember, I pointed out to you that since the shuttle is a glider, energy management is absolutely critical. And so you always come in with a little bit more energy than you're going to need, because it's easier to bleed the energy off through a series of S turns. And then they make the transition when you're essentially Mach 2 or Mach 3, and you're over the landing field, either in Florida or in California. They go into, if this is your landing runway, a regular airplane will typically do a downwind, a base, and then come in for a landing. With the shuttle, we actually want a much larger pattern to give you more opportunity for energy control. So at about 50,000 feet, the shuttle should be essentially overhead, and then it makes a big spiral. And since you're in this big spiral, you have the option of either making the spiral slightly bigger or slightly smaller in order to control your energy. If you're a little bit too hot, have too much energy, then you make your spiral a little bit bigger. If you're a little low on energy, you make your spiral smaller. But by having every landing end in this essentially, it's a spiral which you can adjust the radius, but the basic procedure and navigation is not going to change from flight to flight. So that makes the whole training process much easier. Okay, so you go into the so-called heading alignment circle, and the pilot does have energy displays available, so you get predictors. It tells you where you will be 30 seconds, 1 minute, and 90 seconds in the future. You get a vertical display showing your energy, a horizontal display. Unfortunately, and this is something for the people who are looking at displays, the horizontal and the vertical displays are not well integrated. They had in the talk that some of you heard on the cockpit electronics upgrade, they had some plans to upgrade that and have a unified landing display, but at the moment we don't have that. There is active guidance, so that there are guidance needles which you can fly to, and of course the pilots are well enough trained that they're using their out the window cues as well to make sure that they get the right visual picture, just in case something should be wrong with guidance. Okay, so
This is a ways back, but how much of how noticeable is the big changes in acceleration during like SRB separation or MECO?
Okay, SRB separation, as I said, right before SRB tail off, F equals ma, and the force is pretty much constant at that point, but the mass is decelerating because you're burning, a ton of fuel, over a ton per second. So the acceleration is increasing, and you've built up to about 2.5 Gs when the SRBs finally tail off and you get rid. Then you drop down to about 1 G. Now this is 1 G. You're sitting in your seat. This is 1 G into your chest. Now remember, at this point the shuttle is kind of upside down. So and since you haven't achieved orbital velocity yet, you still have some weight pulling you out of the seat, but you're strapped into the seat, and mostly you feel yourself pulled back into the seat. And of course, as your velocity increases and you get closer and closer to orbital velocity, then the downward acceleration to the Earth essentially matches more and more the acceleration of the shuttle itself, until by the time you're in orbit, you're in free fall. MECO is different. The same thing happens. The main engines are working at maximum, 104% thrust. We don't take them up to the 109, which is emergency only. They're working at 104% thrust, and your acceleration now starts to pick up. After about 7 minutes, you've gotten up to 3 Gs, and the shuttle was designed for a 3 G maximum. They wanted to have a smooth, easy ride for the payloads, and they also wanted it to make it possible for non-professional astronauts to fly on the shuttle as well, the payload specialist scientists. So the engines start to throttle down in order to hold your acceleration to 3 Gs, and they throttle down eventually to about 65%, right at MECO. So you're sitting in your seat, pulling 3Gs, eyeballs in for the last minute and a half or so. 3Gs is not particularly comfortable, but on the other hand, any healthy person can tolerate 3Gs for a minute or two. So it's not a real big deal. There have been concerns if the pilots have to reach some of the overhead switches to reconfigure the ohms or the RCS at 3Gs, could they actually reach it? And some of the shorter pilots decided that they with the Gs they probably couldn't, and so they actually made a special tool we called it a swizzle stick. It's a aluminum rod about 80 centimeters long that has an interface, so you can actually use that, and you have a little mirror if you need it as well, so that you can flick the overhead switches when you're pulling Gs. You can't ignore human factors in these things when you're designing it. If you've really got to flip those switches, and it's not just a problem of being able to reach it. It's also, if you have a helmet on, and when you're pulling 3Gs, your helmet, which may have weighed 15 pounds, now weighs 45 pounds, and so you really can't move your head around very much. And so, just being able to pull yourself away from the seat and look up, you can't do it 3Gs. So you do need some assistance there. In principle, for future designs, I would think taking advantage of the ability to send commands through computers would make a lot of that easier if your computer is within easy reach. This was the early days of fly-by-wire, and people felt that they really wanted to have a hard switch that they could throw. But in fact, in most cases, not all, but in most cases, the switches go through the computer system, and it is possible, in fact, to go into the guts of the computer, and all the switches tend to be multiple pole. I'm getting into some of the details now, but maybe more than you ever wanted to know. But just to give you an idea of the levels of redundancy that they have, every switch has multiple poles, and it's possible that you can get a little solder ball or a little piece of wire, or just one of the pole units, it stops working. So you can actually call up that switch on the computer and disable one or more of the poles, or you can disable the entire switch and take over computer control of the switch. Like I say, most of the switches work like that, not all of them, but it is very much a computer-controlled system. Yeah.
How does the acceleration compare to the deorbit burn?
Deorbit burn is interesting. When 2 ohms engines fire, they only produce about 1/10 of a G acceleration. However, you've been weightless for a week, a month, 6 months, depending what your mission has been, and I'll tell you, everything. The shuttle is accelerating forward, although you're actually going backwards. Okay, but internally, the shuttle is accelerating forward, so everything wants to go aft. And in fact, it's kind of fun. We've done just experiments and taken pictures of it where you can actually pour water at 1 G, at 1/10 of a G, and watch the water slowly go through an arc into a cup. And then, of course, you got to get it closed up before the burn stops. And you can take a little pencil and push it in the y-axis and watch it gradually curve as you're accelerating. It's only 1/10 of a G, but I'll tell you, it feels like you're pressed against the wall if you're not sitting in your seat, just because you haven't been experiencing any acceleration for all that time. And then it gets a lot worse, as you hit the atmosphere. By that time, hopefully, you're sitting in your seat. It's kind of interesting. You know, what I tended to like to do was keep a pencil sort of floating in front of me, and after a while, you see very slowly the pencil is starting to, you know, come down, and then you pick it up, and then it's coming a little faster, and then one of the early things that you realize, you know, if you've seen pictures of people in orbit, your hands are always floating up here. Same thing if you go in a swimming pool, just hold your breath and float underwater. Your natural, total relaxed body position is sort of bent over a little bit, and your hands are out front. You know, try it sometime. It's quite relaxed, quite comfortable. And it was a strange feeling. You know, again, I got used to it after my first entry, but the first time when I realized that I was sitting in my seat and my hands were actually in my lap, you know, and that hadn't happened. You know, I'd realized all the time before that your hands are sort of floating out there, and then I reached for the camera to take a picture out the window of the shock waves behind the shuttle, and all of a sudden, you know, geez, it's got weight, and it's amazing how the human mind can get used to a very bizarre situation, you know, like weightlessness, such that when you get back, it's you know, it feels strange. It doesn't stay strange for long. I mean, you grew up in 1G, and your body has a pretty good memory, so it doesn't take long to get back. But there are potential vestibular problems. We have people in the Manned Vehicle Lab have spent their lifetimes studying some of these phenomena. You know, a lot of your orientations for up or down come from your inner ear, which have gravity receptors. Well, those basically don't work very well. They don't work at all because the gravity is you know, the little bone particles inside there are basically floating around, so you don't get the proper feedback. But you still get visual feedback, and you get rotational feedback from your inner ear, and so your body has to essentially reprogram the feedback loops so that you can maintain your sense of orientation, and that leads to space sickness. In about roughly 2/3 of people who go up experience some form of space sickness, sort of like seasickness, anywhere from mild enjoying the feeling of weightlessness. But launch is really an overwhelming experience, with all the vibration and the power and the acceleration and everything. And I remember thinking to myself at MECO, when I started floating, I thought, oh, now I'm in an environment that I understand, because I had so many 135 parabolas that the feeling of being weightless was not as overwhelmingly new as it otherwise might have been. Although what I realized after about a minute, I was sort of holding on to the seat waiting for the pullout, and that's when I realized, no, wait a minute, no pullout, you're really in orbit. And that's when I got really excited and sort of floated over to the window, and I basically couldn't wipe the smile off my face for about 7 days. But anyway, yeah.
What about the internal clock? Do you still have 24-hour days, or?
Yeah, basically, the sun rises and sets every 90 minutes. What we try to do, this wasn't done in the early shuttle flights, but often you have to launch at odd hours if you're doing a rendezvous, particularly. So, for instance, when we launched to repair Hubble, the launch was 4 a.m. because that's when Hubble happened to be flying over. So now 4 a.m., typically your body is at about its lowest point in the 24-hour cycle. Your basal metabolism, your temperature, not the condition you want to be in when you go through a launch in case there's any problems. So what you want to do is adjust your sleep cycle. It's very hard to adjust your sleep cycle when you have, the sun rising and setting every 90 minutes, because you don't get any light feedback. But what we do is, starting a week before launch, the crew goes into a medical quarantine so that you don't get exposed to any cold germs, because you don't want to get sick on orbit. And so at that time, what they've done is use some medical research over the last 20 years or so, which indicates that bright lights can actually help. Bright lights at the right time of day can help your body change to a new time zone. That's why they say when you fly over to Europe, you fly overnight, you don't usually sleep too much in the airplane, you land early in the morning, and a lot of people then want to go to their hotel and go to sleep for a while. But the doctors tell you that's the worst thing to do as far as getting used to the new time zone. What you really want to do is go stay out in the bright sunlight at a time when your body thinks it should be dark, get the sunlight into your brain, and that's what we do. In the quarantine quarters, everything is white. The tables have white butcher paper, and the walls and the ceiling are white, and there's essentially wall-to-wall fluorescent lights on the ceiling. And so it's really bright. I mean, you have to wear sunglasses when you first go in the room, and it's too bright to watch television or even to use your computers. But it works. And after about 2 days, you're pretty much accommodated to the new time. And then if you want to go out during the day when the sun is out, but it's a time when the sun shouldn't be out, for the time you're trying to switch to, you have to wear really, really dark sunglasses so you don't get deprogrammed. The problem is sometimes when you're on orbit, because of the precession of orbits, you tend to have to re-enter on a short shuttle flight. This is different for the space station, but on a short shuttle flight, you typically re-enter a few hours earlier than your equivalent launch time, and that means that you have to often do a sleep shift in orbit. And that's much more difficult, particularly if you try to shift earlier. It's relatively easy to stay awake for an extra hour and then wake up. I mean, everybody likes to lie in bed for an extra hour. That's easy. But to go to bed an hour or 2 hours early, it's hard to get to sleep, and then you have to wake up 2 hours early. That's difficult. But that typically is what you have to do. And so the medical people have actually imposed maximum shifts both per day, per week, and per month, for how much the crew can be asked to shift their sleep schedule. The Russians have another problem when they do spacewalks. Because they don't have a full equivalent of a TDRS system, tracking and data relay system like we do. They like to be doing their spacewalks when they're making passes over Russia, so that they can get ground tracking. And so often when a Russian crew is preparing for a spacewalk, they have to shift sometimes by 8 hours at a time, and it can be really tough on a crew to have to do that. If any of you have worked third shift on anything, or it's not like pulling an all-nighter where you eventually the next day you go back onto your normal shift. To actually stay on a different shift for 3 or 4 days at a time can be tough when you don't have any light cues to accommodate you. Yeah, you gotta.
Oh no, it's just an observation that I guess that all those measures to shift the sleep cycle is obsolete now with the no night launches, right?
As long as there's no night launches, that's probably true. Yeah. And what that means, of course, is that they can only launch to the space station at certain times of the year. That's the price you pay. Yeah.
On the launch pad, what's supporting the entire weight of the orbiter? And secondly, if you're on the mid deck, are there any windows? And if not, can you see? How do you know?
Okay. I should bring in the launch bolts. I have a couple in my office. The entire weight of the shuttle stack is supported on the 2 solid rocket boosters. So the bottom skirts of the boosters are actually sitting on the launch pad. And so there are, on each of the boosters, there's 4 big nuts and bolts, 4 on each booster. They're explosive nuts, and at the moment that the solid rocket boosters ignite, all 8 of those nuts are split in half so that the boosters can lift off. Now, I asked the question, what would happen if one of them didn't go? And the answer was, well, we think that the booster is strong enough it would just rip it out, but nobody wants to find out. And obviously, these are redundant explosive bolts or nuts. They did have, on one flight, they found that 1 or 2 of the redundant firing units did not fire, and that got people's attention. And I don't know what the final resolution was, but it's that's basically, those bolts are, if there's wind blowing and the shuttle is rocking back and forth, all of that load is taken through those bolts. So the structure of the solid boosters has to be able to accommodate that. You asked me another question as well. Oh, the middeck. There is the hatch where the crew gets in has a window in it. Before Challenger, one seat in the middeck was right next to the hatch. So my first flight, I actually sat next to the hatch during ascent downstairs, but I had a great view out the window. Now, after Challenger, we have an ejection pole. It's a telescoping pole which is suspended from the ceiling. I think we talked about this before. How if the shuttle is in a situation where it's in stable flight, but you can't make it to a runway at about 40,000 feet, you blow the hatch, the telescoping pole, you release the pin, the pole will extend, then you one by one you clip onto the pole and you jump out, and the pole takes you below the wings so that you won't hit the shuttle structure, and then eventually your parachute will open. So that now takes up the area over by the window, and the 3 seats no longer have a view.
So how do you know, if you're sitting on the middeck during launch, how do you know what's going on? Is it only through comm?
Yeah, you hear the comm loop, and you know, if you have a nice commander, he'll tell you, for instance, if you have a rookie astronaut on board, they want to know when they go through 100 kilometers, because that means you've officially been in space and you can get your astronaut wings. So if the commander is nice, he'll call 100 clicks on the way up and congratulate the new rookies. But basically, that's about it. And the same for entry. You know, you don't have a view. There's still plenty of physiological things to keep your attention. So it's not like it's a boring ride, but you know, you don't have the view. Okay, well, let's let me run the entry picture here. Okay, Ohm's engine ignition is when you see that big flame pattern. During the burn, you don't see anything. Now, looking out the front, you see the plasma sheath goes from a dull red to gradually to orange, and then eventually white hot. You can only see this at night. It's fairly faint. But typically, a lot of flights you land during the early part of the day on the ground, and of course, you do your burn halfway around the world. So the early part of your entry is very often at night, and then you fly into the day. And then I think there's another shot looking out the aft window where you actually see the wake, the plasma wake, in the back of the shuttle. And you can see this is the old-fashioned computer screen with the vertical. Yeah, so that's the wake looking out the overhead window. And where these converge, that little point there, they say that's about 10,000 degrees Fahrenheit, which is the surface temperature of the sun. It's remarkably stable, although every once in a while you get those instabilities, and every once in a while you get big bright things go flying past, which I assume are gap fillers coming out. And I remember I would always think to myself, yeah, I hope that's nothing important. But so that's yeah, you're basically riding on a meteor, or meteorite, because it's supposed to make it all the way down to the Earth. But that's essentially what you're seeing, is that trail behind you. And I'm sure you've all seen these landings. Remember all the talk about the landing gear and the brakes. I looked for a video from my first flight to show you the blowout, and if I couldn't find one, but if I find one, I'll bring it in and show you another time. And this is a landing out at Edwards.
Have you ever landed at night?
I've landed at night, yeah. I was going to show you one other.
It doesn't have a landing light, does it?
No.
Light the runway, or just?
Yeah, they have two banks of xenon lights. Let's see, here's eject, which light up the runway for you. Okay, so this next video is from my last flight where we deployed the tethered satellite. I'm not going to show you all that stuff, but I wanted to show you the launch sequence, because we have a few pictures showing the opening of the payload bay doors, and then you can actually see back to the aft end of the shuttle where you have the main engine. And remember I talked about how the hydrogen and oxygen have now combined into water, and that forms ice. And so for the first day or so on orbit, there's just constant ice particles coming out of the engines, and you're surrounded by this cloud of ice, which unfortunately the pictures are black and white because it's low light level TV, but visually it's spectacular, because these little ice particles glint in the sunlight, and they're rotating, so they kind of they go through all the different colors of the spectrum, and you're surrounded by this. You also see one of the RCS jets firing. So we'll just run through the okay, water deluge, main engine sequence. Again, you see the whole tilt. When it gets back to vertical, we take off. This is a much shorter sequence here for the launch than the last one.
How does it roll? What's
The SRB boosters go like that.
Is it the entire stack or just the lower?
No, it's just the nozzle at the bottom. Okay, this was Columbia. You can always tell Columbia because if you look at the vertical stabilizer up here, that's an infrared pod. I'll talk about that in a minute. The payload bay doors open right away, and so now you can see when we've done the engine vent, you can see all the ice particles coming out, and you'll see a primary RCS thruster going there. So it can be pretty spectacular. And that just keeps going for about a day, and then you've got rid of most of the ice particles. Okay, so that's enough of that. Yeah.
It seemed to have a pretty large effect today.
Yeah, no, that was a primary RCS thruster.
Did they disable that for like spacewalks and stuff?
Yeah, absolutely. No, in fact, all of the vernier thrusters are downward thrusting only. So remember we talked about with the primary thrusters, they were designed and sized for rendezvous, where you actually have to have controlled propulsion. And if you want a Z, propulsion of the shuttle, you want to be able to get a pure Z. So you fire thrusters on each end, and the same for roll and yaw. And you don't want a lot of cross coupling because you're targeting your burn to fractions of a foot per second in order to get your rendezvous to come out right. And so that's when you're using the primary thrusters. Other than that, the primaries use a lot of propellant, and so we disable the primaries and use the verniers. So with the verniers, there's two verniers in the nose which are sort of canted down at about 45 degrees. And in the rear, there's two pointing straight down and two pointing straight out. So typically for a given maneuver, you'll fire only one or two. If you want to do a roll, for instance, you'll fire the 45-degree down forward thruster and the downward pointing aft thruster, and but they're not completely balanced. So you'll get a little bit of pitch and a little bit of yaw. And when you're trying to do, you don't use the verniers for propulsion at all. Although, because all of the verniers are essentially downward firing, if you are, for instance, station keeping, if here's the space station and you're in the same orbit, but say, half a mile in front of it, now you're station keeping using your vernier thrusters, typically that does give you, after a while, a little bit of propulsive maneuver which pushes you in, so you have to compensate for that. So the verniers are single string, there's no redundancy, they do have axis to axis cross coupling, they're designed for attitude control only, 25-pound thrusters, reasonably efficient. I thought at the end we could explore a little bit together some of the ideas of improvements to the shuttle, which you're going to be thinking about. And one of the things that I thought would be interesting to think about, we talked about the fact that if you're designing the shuttle to the same set of requirements that were originally put on it, your ability to change some of the major physical characteristics of the shuttle are very limited. We can do a lot with electronics and some of the other systems. But suppose the new vehicle, the crew exploration vehicle, is being designed not just to go to Earth orbit, but they want a vehicle that can actually return to the Earth from the Moon or from Mars. That means instead of a orbital velocity of 5 miles per second, you have a re-entry velocity of a hyperbolic velocity of about 8 miles per second. Does anybody remember the relationship between low orbital velocity and escape velocity? If your low Earth velocity is v, what's your escape velocity? Square root of 2v. That's a nice thing to remember. It's an easy way to keep those things straight. We don't have to have a winged vehicle, first of all, you don't need wings to go to the Moon. They don't do you much good when you get there. And to have a winged vehicle that you can thermally protect against hyperbolic reentry velocity, it just doesn't make sense. It would be too heavy. We don't think we can do that. And in fact, I wonder, the Russians are now talking about building this new Clipper vehicle, which possibly will have wings on it or be a lifting body. And that actually probably means that they will only use it for low Earth orbit. But it does bring up the interesting question. If you are designing a vehicle that only can go to Earth, that is only designed to go to Earth orbit as a passenger carrying vehicle, one of the first things that we ought to ask ourselves if we're doing a new design is, should we have wings? So think a little bit about the advantages and disadvantages of wings. If you're sitting down now with a blank drawing board going through a design process, first of all, what are the advantages of wings? You've heard quite a bit about shuttle aerodynamics, and what advantages do you get from using wings during a re-entry? And obviously, it's only during entry that the wings are going to help you, because they're a real nuisance during ascent. Greater cross range. So cross range helps with the wings. The glide. Yeah, it allows you to land on a runway. So you don't, in terms of having to design against the shock of the crew exploration vehicle is going to land with parachutes, and they still don't know, are they going to use airbags or retro rockets or crushable structure or whatever. They don't know, but it's going to take a much harder hit that may potentially affect reusability, maintainability. Okay. Don't know how much. Yeah.
I was going to say, just purely control while coming back in. You can probably like a cross.
Well, we had the cross range, but on the other hand, the
targeting, I guess, too. I mean, even if you
targeting,
land, say, in a certain part of the desert,
right,
Mexico, you'd want to have a lot more accuracy.
Right, and so for the CEV, they're just basically saying they're going to land out in the western desert somewhere. Now, the Apollo shots were getting pretty accurate. The last couple of Apollos landed within visual range of the aircraft carrier that went to pick them up, so they were getting pretty good. But that's within a couple of miles, which is fine when you're landing in the ocean, and maybe it's okay if you're landing in the western desert. It's certainly not okay if you're going to land on a runway.
Hardly an engineering consideration, but how much thought in the design was put into making it a winged vehicle for it to be a comfortable, familiar look to people, especially if the idea was to have non-professional astronauts fly. You know, it seems more comfortable to get in something that looks like an airplane.
I don't know about comfort from that point of view, but there's no question that the whole aviation metaphor dominated discussion in the early days, and I think you've gotten a sense of this. You know, the idea was we want a reusable vehicle. That means we have to have airline-type operations. Well, you know, if you're going to have airline-type operations, then you want a vehicle that lands on the runway, you take it into the hangar, you turn it around, you launch it again, and I mean, it's a very powerful metaphor. What are some of the disadvantages of wings? You know, what are some of the things that argue against wings? You know, again, we're going right back to the conceptual design exercise here, and this is not what you're doing for your papers, because you know we're totally changing the concept of the shuttle. But you know, for the purpose of the class, let's think it through. What are the disadvantages of wings?
I think a lot of what we talk about is initial design costs versus, and no wings obviously has a lot less initial design costs because you don't have to design the structure to support the wings, and it's a lot simpler design, I think. So that probably saves you money in the initial development.
Heating is probably one of the biggest issues from an engineering standpoint. The less stuff sticking out from a big cylinder, the more problems you're going to have.
Now, on the other hand, I don't know how much any of you have studied the theory of reentry bodies, but the reentry of a ballistic capsule typically gives you much higher G's than you can get with if you have a lifting body, and of course with wings you get much more lift. You can actually decrease the G loading, so that with the shuttle we can have a re-entry pulling no more than about 1.5 Gs, whereas you come back in a capsule, even from Earth orbit, from low Earth orbit, and you're going to be pulling 4, 5, 6 Gs. So it gives you, and that does relate back to the idea that we wanted the shuttle to be able to take much more delicate payloads and hopefully take people who were not necessarily trained astronauts. So that's, again, it's an advantage, but a disadvantage of wings. The area of under the wings is huge. So, that puts huge demands on your thermal protection system. With I don't know what they're going to end up using on the CEV, but it's going to be a much smaller area that has to be protected. Another interesting thing when you think about wing vehicle like the shuttle, now I know that Buran, the Russian shuttle, made its one flight unmanned. They had some tense moments at the end, but they did manage to land it successfully. But the way we fly our shuttle, we have to have 2 trained pilots who spend a tremendous amount of time doing nothing but learning how to land the shuttle. So sometimes we don't think about the crew requirements on the design, but training is not an insignificant part of the cost of operating the shuttle. There's a huge enterprise involved in training astronauts. And training pilots particularly is very expensive. You have to keep them qualified as pilots, so NASA maintains a fleet of T-38 supersonic jets, which are great fun. I mean, I love to fly backseat in them, but the only justification for having them is if somebody's going to be a pilot, they gotta stay current as a pilot, which means you got to fly. And we have the shuttle training aircraft, which I've spoken to you about, and we have all the simulator time, all just, and then we have the problem that people said, well, there was a time when they were talking about having the shuttle spend extended periods of time up at the space station. a month, maybe 2 months, make some adjustments to the shuttle system so you could do that. Then the problem is, well, who's going to land the shuttle? Because, I talked to you about the spatial disorientation and everything that you feel during re-entry. Well, you don't want a pilot to do that. And if a pilot's been up in the space station for 1 or 2 months, hasn't had any stick time, is going to have potentially serious neurovestibular problems during entry. And so it was a real question, is what's the maximum time that it's okay for a pilot to spend in space? We'll never actually have to answer that, because 17 or 18 days was the maximum shuttle mission. That turned out to be okay. And we're never going to do long duration missions with the shuttle to the space station. Yeah.
With the ballistic capsule, you still have the same problems.
No, because you don't.
The pilots still spend a lot of time learning how to.
But they learn a lot of the malfunction procedures, but you don't actually fly the ballistic capsule. I mean, I'm not in any sense denigrating the training that the Apollo astronauts needed to land their capsule, but it didn't compare in the least to the amount of training, for instance, to land on the moon, where you were actually piloting the vehicle. So, okay, well, I hope just that very brief exploration, will make you think about, designing new vehicles from a slightly different point of view. In other words, when we designed the shuttle, it was just assumed as gospel, essentially, that if you want a reusable vehicle, put wings on it. I don't know what the right answer is. It probably depends on some of the details of the mission, but you really have to go back and question your most basic assumptions when you're doing your concepts and you're setting out your requirements. You don't want to write your requirements in such a way that they presuppose the technical solution. So if you write your requirements for a winged vehicle, you've already shut down a whole part of design space, and as designers you don't want to do that. Yeah, last question.
Have there been any capsule vehicles that they've attempted to reuse?
No. The Russians have actually taken, my understanding is they have taken some of the electronics out of capsules and reused internal parts, but the exterior shell of capsules I don't believe have ever been reused. Okay, we'll see you Thursday. Bob Reed is going to give a talk on aerothermodynamics, and I'll look forward to seeing your journals. Any questions on the reports, the outlines that I returned? Email me, come to see me. I'm happy to talk with you about it.